Okay, example number 4, another angular momentum example. We have a diver jumping off a diving board, tucking, and they're able to spin easier because their mass is closer to their axis of rotation as they spin into the water. We're going to look at this, what happens if the diver remains untucked and arms and legs extended out in the air. So their rotational inertia is smaller when their arms and legs are tucked versus when they are spread away from each other. So we are going to use conservation of momentum, in particular conservation of angular momentum here, to figure out the angular speed of the diver when the diver is untucked. Now, above here I have my momentum equation, but when we look at this, our system is the diver, the, the external object is the Earth, but the Earth pulls at the center of mass. So when a person dives into water, they rotate about their center of mass, which means here there will be no external torque because the distance from the force of the earth exerted to the center of mass is zero because the force of the earth is exerted on the center of the mass of the person. So we don't even have to worry about angular impulse, which means the initial angular momentum of the person will also be the ending angular momentum of the person. So in our initial picture, we have the diver tucked. So the angular momentum of the diver tucked times the initial angular speed will equal the final angular momentum of them untucked, essentially when they move their arms and legs apart. So we have 3.6 times 12 radians per second is equal to 18 when their arms are spread apart. So numerically, all right, you almost increase here by a factor of 5 by just taking your arms and legs and spreading them away from your axis of rotation, multiplied by the final angular speed. So if we solve for the final angular speed, we find out that the final angular speed is 2.4. This idea, okay, compares to that which we discussed in class, where if your arms are close to the axis of rotation, it's easier to spin. If they're further away, it's harder to spin. There's no external torque. It's simply, but instead of changing, you're essentially changing what would be the equivalent of mass here, but it's not mass because the mass of the person stays the same. You're just taking the mass of the person and spreading it further away from the axis of rotation. That will constitute a change in rotational inertia, which in turn changes the angular velocity. And we can use conservation of momentum to find this answer out.